In this video, we'll generate the trendline and trendline polynomial of the Gaussian integral using ERF Gauss function, complementary error function, and the NORMSDIST function. We begin the Taylor-Maclaurin SERIESSUM of the Gaussian integral, which is the summation of a times x to the power 2n plus 1, and the value of a is negative 1 to the power n over n factorial times 2n plus 1, where the value of n starts from 0 up to infinity. And we continue with the coefficient, which is equal to ARRAY formula minus 1 raised to the power n all over. There are two parts, factorial n, that's factorial n, and the second part, so times the quantity 2n plus 1, 2 times n plus 1. Enter. Now we can complete the Taylor-Maclaurin SERIESSUM expansion of the Gaussian integral. So ARRAY formula SERIESSUM of the x values raised to the power 2n plus 1, where 2n plus 1 starts from at n equals 0, that's 1, and interval. So that's 1, then 3, then 5, and 7, and 9. So the interval is 2. And the coefficient will be this range. And here you have the trend line and the polynomial, trendline polynomial of the Gaussian integral. We continue with the error function, which is equal to ARRAY formula ERF of the x values. And the Gaussian function, which is ARRAY formula Gauss of the x values. And the complementary error function, ARRAY formula ERFC of the x values. And finally, the NORMSDIST, ARRAY formula NORMSDIST of the x values. Okay, then we work on the error function. So what we need is we multiply 0.5 times square root of pi. So we multiply ERF times 0.5 times. And then multiply this by square root of pi. So times square root of pi. Now their data sets are the same. They're on the same trend line. Let's move this a little to the left. And their polynomials are the same. They're the same polynomials. Next, the Gauss function. The Gauss function multiplied by square root of 2. So times square root of 2. Next, multiply by square root of pi. So this will be times square root of pi. Now all three are in the same trend line. Their trend line equations are, their trend lines are on the same trend line. Their data sets are the same. And their polynomials are the same. Next, the complementary error function. Here we have minus 1. So start with the negative x. So the green has changed. Then factor in minus 1. So minus 1 plus error function. Now they're together. And finally, multiply by 0.5 square root of pi. So 0.5 times the quantity. And finally, the square root of pi. So square root of pi. So times square root of pi. Square root of pi. There. Now they're all in the same trend line. Their data sets are the same, and their polynomials are the same. This is 0. That's very small. Negative 9.24 times 10 minus 47. This one is also 0. Negative 2.22, but 2.22 times 10 to the minus 16. That's very small. That's already 0. Negative 5.07 times 10 to the minus 16. That's already 0. And 2.9669 times 10 to the minus 16. That's already 0. And 3.88 times 10 to the minus 17. That's already 0. All these non-zero coefficients are the same. And finally, the NORMSDIST. The NORMSDIST, we begin with the square root of 2. Square root of 2x. So times square root of 2x. Then factor in minus 0.5. So minus 0.5 plus. And finally, multiply by square root of pi. So square root of pi times quantity. Now they're all in the same trend line. Their data sets are the same. Their polynomials are also the same. This completes the use of array formula, error function, Gauss function, complementary error function or ERFC, NORMSDIST function, and Taylor Maclaurin series sum factorial to generate the trendline polynomial